Hello, this is Mrs. Taylor, and I am going to walk you through a problem where we are trying to make a piecewise function differentiable by finding values of some constants. In this particular problem, f of x equals x cubed when x is greater than or equal to 1, and it equals a times x minus 2 all squared plus b when x is less than 1. And when I'm trying to make a function differentiable, I first need to determine, especially with a piecewise, if it's differentiable at each piece. So x cubed, I know because I'm familiar with my parent functions, x cubed is a smooth curve. There's no discontinuities, there's no cusps or corners. So I know that x cubed by itself is differentiable by being familiar with its graph. This function here with the a and the b constant, if I multiply all that out, I'm just going to get a quadratic function that I know forms a parabola. And again, I know what a parabola looks like. I know it's a smooth curve, it has no discontinuities, it has no cusps, it has no corners, so I know this piece on its own will be differentiable. The only place in question where this piecewise function would not be differentiable is at x equals 1. Okay, so I'm going to note that over here. Possibly not differentiable at x equals 1. Okay, so that's where I want to work. I want to work so that my a and b equal values so that it is differentiable at x equals 1. And when we're talking about piecewise functions and differentiability, we know that at the point in question, my left-hand derivative and my right-hand derivative have to be equal. So that's my strategy for finding the values of a and b. I set up my left hand and my right hand derivatives, and I set them equal to each other, and then I solve. So that's what we're going to do. And because my handwriting is terrible and this is going to be a lot of algebra and notation, I'm going to type these in. So to start out, let's write out our left hand derivative using the limit definition. So here is our setup for our left-hand derivative. Its limit as h approaches 0 from the left of f of a plus h minus f of a over h. And you may notice that this is the limit definition for the derivative at a point because we're only looking at where x equals 1. And so if I write that out using the function So if I write that out using the left piece of this function, that would be values less than 1. So I'm going to use the a times x minus 2 all squared plus b for my left-hand derivative. And if I write it out, it would look like this. First, we would have our a value, which is where we have this possibly not differentiable point, and that would be 1. So I plugged in 1 for a, and now I have to input the 1 plus h into the function and the 1 into the function. And so this is where things can get a little mixed up because there's a lot of variables going on. So I'm going to type this out as I talk through it. So in my setup, I know I'm going to have the h in the denominator, but how do I write out this numerator? So the thing I have to remember is this 1 plus h is the input for x, and that's it. So the only thing I change when I write this out is the x. So I'm going to type it out exactly like it is here, except when I see an x, I'm going to put 1 plus h. So I have a, and then I have x, which would be 1 plus h, and then I have this minus 2 here, and then parentheses, and that's all squared. So I need to make that all squared. plus b. So don't forget, when you get your get involved in this input process, make sure that you go step by step, term by term. So I have my a, I have my x value, which is 1 plus h, minus 2 all squared, plus b. Okay, so that's only f of 1 plus h. And then I have minus f of 1, which would be the, substituting 1 in just for x. So what that would look like is minus, and I'm going to rewrite all of this like it is, but instead of x, I'm going to put 1. Because we have this plus sign, I'm going to start off with parentheses, so I know it's minus all of this. So I have a, and then instead of x minus 2, it would be 1 minus 2, and all of that would be squared. And then plus b. Always check that you've got everything plugged in correctly. So we have minus f of 1, and that would be a parentheses, and it's not x anymore, it's 1 minus 2 squared plus b. So once I have everything substituted in for my f of 1 plus h and my f of 1, it would look like this. At this point, I need to simplify. So over here I have this 1 plus h minus 2 all squared. Need to multiply that out. And then over here I have this minus the 1 minus 2 all squared times a. I need to reduce this down and simplify it. So here we are. I have 1 plus h minus 2, and I know 1 minus 2 is going to be negative 1. So I'm going to modify that to be minus 1. And it's going to be squared. So you're more than welcome to, off to the side, scribble out what h minus 1 all squared is. Or if you feel confident doing it in your head, you're more than welcome to do that as well. I'm going to attempt to do it in my head. So h minus 1 all squared would be h squared minus 2h plus 1. So let's see. So that would be h squared minus 2h plus 1. And then over here I have 1 minus 2, which is negative 1, squared, which is 1. So 1 times a is just a. And then distribute the negative, so that would give me minus a and minus b. And then I have b minus b, so those would then cancel each other out. And let's change this plus minus to just minus. And let's have that simplified next. Okay, so from there, I'll distribute the a. So this would become ah squared 2ah plus a. So just distributed. And now I have this. And now I can see I have a minus a, so those would cancel to 0. So this is where I'm at with simplification. Uh-oh, forgot my parentheses. A squared plus 2a. Now, at this point, I can see that I have an h in each term. So h squared would become just h, and then 2ah would just become 2a. So this exponent would go away, and I'd be left with the h, and then this h would go away, and then the h in my numerator would go away. So I have ah minus 2a. So let's get rid of all that. And then using direct substitution for 0 or plugging 0 in for h, I end up with just negative 2a. So my left-hand derivative equals negative 2a. A lot of work, huh? Now we're going to repeat that process for the right-hand derivative. So for the right-hand derivative, I have the same setup as before, the limit definition for derivative at a point, and then when I use my a value, I get the limit as 0 as h approaches 0 from the right is f of 1 plus h minus f of 1 over h. So now I'm going to plug those values into my function, or excuse me, yes, my function that's defining this piecewise function from the right, which would be values greater than or equal to 1. So I'm going to use x cubed. So what it would look like is this. So I would have the limit as h approaches 0 from the right of 1 plus h all cubed, because I have x cubed, and I'm inputting the 1 plus h in for x, and then minus f of 1. Well, 1 cubed is just 1. And so then the next thing I need to do is cube 1 plus h. And for the sake of time, I've already multiplied all that out on a separate piece of paper, and I'm just going to type out what that is. But you can go back and cube that yourself. Once it's multiplied out, 1 plus h cubed equals 1 plus 3h plus 3h squared plus h cubed. And then I brought this minus 1 down. So what ends up happening is the 1 minus 1 cancels. And then I have an h in each term in my numerator. So when I factor 1 out, I get an h out of here. H squared would become just h, and h cubed would become h squared. So when factored, I would be left with 3 plus 3h plus h squared, and the h's that you factored out from the numerator and the h from the denominator would cancel. So my limit would look like this. And then when I plug in 0 through direct substitution, I just end up with 3. Whew, that's a lot of work. Now, I'm still not done because I still haven't solved for a or b. The whole purpose of this was so that we could get our left-hand derivative and our right-hand derivative equivalent. So at this point, I would take my left-hand derivative and set it equal to my right-hand derivative. And so I'd have negative 2a equals 3. And then when I solve for a, I get 3 over negative 2, or negative 3 halves. So a equals negative 3 halves. That's part of it. But now I have to find b. And so I need to slide some things out of the way first. So I'm thinking, we've done all this work for our left and right hand derivatives, and we've arrived at the two derivatives, negative 2a here and 3 here, and so I set them equal to each other, and I solve for a. So now the most important thing out of this is what a equals. So I'm just going to flip over here and get rid of all that other work so that we can start fresh. Now the question is, where do we go from here? Well, remember, if it's differentiable, it has to be continuous. So that means I can use this negative 3 halves now in for a, and use the fact that these two pieces have to meet at the same y value to solve for b. So if I plug 1 in for x and -3/2 for a and set these two pieces equal to each other, that will allow me to solve for b. So that's what I'm going to do. So it would look like this. I plug 1 in for x cubed, I get 1 cubed, and then a is -3/2, x is 1, and b we are solving for. So when I reduce everything out, down, or simplify rather, 1 cubed is just 1. 1 minus 2 is -1. -1 squared is +1. So I have 1 equals -3/2 plus b. So 1 equals -3/2 plus b. Okay? And then, of course, to continue to solve for b, I would add 3/2 to both sides. So 1 is 2/2, and 2/2 plus 3/2 would be 5/2. So b would equal 5/2. So now I have my two solutions. A equals -3/2 and b equals 5/2.